Hey guys, John Grimsmo here. I've got a quick little video for you. I'll try to speed through this. This is a Bloom TC52LF touch probe, a spindle probe. This device at the tip deflects and measures and can infrared send the signal back to the machine. No wires or anything, it's all wireless. That can tell, oh, I probed a surface, it's exactly 1 inch tall, or I probed a hole, it's this diameter, or this feature or that, or I use this so much for everything. I made a little goof last night and I broke the tip. It's not big, I mean this thing is delicate. It's a 1mm ruby ball and a less than 1mm carbide shaft. It's delicate. And so I go looking through all my current stuff, looking for the replacement, and there's no replacement. I don't have an extra one. Ugh. So this happened last night, literally just as I'm about to start or continue. It was 22 hours into a run, and it was going to continue for another 15, 16, 17 hours, which would have gone from my record of uninterrupted cycle time. But I made a goof, and the tip broke mid-cycle, and yeah, so I had to rush and try to find a replacement. So immediately I texted my buddy Mike from Milterra, and he said talk to Jean from inspectshop.com. Check out the website here real quick. This is not a plug, I'm just giving this guy a shout out because he hooked me up immediately. That was late last night, I emailed him right away. He was here at 9 a.m. this morning as a favor, like to hand deliver them. He wouldn't normally do that, but awesome guy, and I bought 4 replacement probe tips because 1 is none, 2 is 1 is none. Look at that, $38 for this silly little guy that stopped my production. It stopped my machine for the entire evening. I couldn't do jack. The machine is useless without the probe because I use it for absolutely everything. I use it so much that if this doesn't exist, I just turned the machine off last night, which is rare. It happens, whatever. I've learned my lesson. I'm trying to teach you guys the lesson too. So the one that I've reinstalled back on the probe doesn't exist anymore in my mind, and now I have 3 more on the shelf for 3 more mistakes, which is good. And then these are the ones that we use on our Mori and our Nakamura. It's a 2mm ball with a 50mm shank. And same thing, about the same price. Now we have 2 on the shelf and 1 in each machine, so we're good. They don't wear out, they just break due to a problem or a dumb mistake. So I want to show you guys real quick how I set this thing up. Okay, let's put this thing back where it belongs. Notice there's a front engraving because this one has these, right where my thumb is, and one more on this side. These little locating brackets right there. Just number 20 has this extra little locator so that you always put it in the exact same orientation. All of the other ones don't have that. You can get them, but it's not needed. But with this one, you want to clock it always the same. So I've replaced that. Now let's call it up in the spindle. Okay, MDI tool call touch probe in Z, spindle speed 0. Cycle start. Wait for it. Okay. So when you replace a probe tip like this, there's a couple things you need to check and make sure that are dialed in. One is the circular runout as you rotate the probe, that the ball is exactly in the center, and there's 4 adjustment screws, just like a 4-jaw chuck, that let you kind of position it until your dial test indicator that's on the tip reads 0. So I got to do that, and then you also have to reset your tool length from the spindle face, your gauge length, down to here. It's about 5.3 inches on mine, but with a new tip it's bound to be just a little bit different, so we'll get into that in a minute. Here I have a Noga magnetic base mounted just to one of my steel fixtures, Mitutoyo 10th indicator, dial test indicator. So I've got it set to 0, it's lined up with the probe, and then let's see what the runout looks like as I rotate the spindle. Oh man, it's actually off the needle right now, and then I keep rotating and it comes back on the needle, and that just happens to be my high point. Okay, so not surprising, but not ideal. I would never run it like this. So now I just have to loosen, I think, the 2 set screws on the 2 sides, and then the 4 little jack screws, and let it get concentric until it's dialed. And then I just keep messing with it. This is a 2 to 72 minute fiddling process. Check this out. For a cool filming angle, I learned how to open that door. You have to enter a special service menu on the Kern. That you can't run the machine like this, but I've opened that door. Now I can open this door, and then I can put the camera right there and see what's going on. Oh, yay! Here we go. Hello, everybody. Needs more light this way. Oh, that's pretty cool. So I just happened to be on Instagram this morning and saw a comment that said somebody was doing this as well, and they said big shout out to ABOM79 for showing the video on YouTube how to indicate a 4-jaw chuck. Now I've done this many times and I've probably seen that video, but I'm going to go watch that video again just to refresh, because adjusting 4 bolts, it's weird. And I think he's got the perfect recipe, so I'm gonna go check. So watching those YouTube videos pretty much confirmed what I knew, what I thought from my experience. However, I'm never afraid to just jump on YouTube and get a refresher. The information is all out there. People have already done it. They're much better at explaining things than I am. Helpful. But yeah, you have 4 screws, and basically you want to find your high spot there, for example, or you want to split the difference, one guy was suggesting, which is a great idea. And then from the high spot, you want to find the 2 adjustment screws and push it that way or this way until 0 and 180 are relatively 0, and then you rotate it 90 degrees and you get those 2 screws and you get it in. It gets a little tricky when you want to be perfect. There's a lot of fiddling back and forth, but it's got to be perfect. Notice how it's not on 0, but that does not matter. This is all a relative movement. We're looking at how much that needle moves as I'm rotating. I want to make sure you see I am actually rotating. Nice, that is good. I can, if I look real close, I can see it. If I look real close, I can see it moving ever so slightly. So maybe I could get a hair better. And also once I properly tighten everything down, especially the 2 pinch screws on the side, it tends to all go out again. So you got to be careful about that. As perfect as you get it when everything's loose, it's going to change. So there's some fiddling back and forth. So exactly what I was saying. I had it perfect, and then I tightened the 1 tightening screw on the top, and now it is what, 7/8 thou out. I'll get it. All right, I got it. It wasn't actually that hard. Didn't take too long. It is tight. It is dialed. It is perfect. Now, technically, I think, especially on this machine, but on many machines, there are calibration settings where the tip does not have to run perfectly centered, because if you probe a bore with a very known location and the ball is off, the machine will know that it's off, and it will compensate for that. There are compensation factors in the tool table or probe table or whatever. So if it's off by 2 thou in X, it'll know that. So maybe it doesn't have to run through perfectly, but every little bit of perfection you can add to a process only adds to the perfection of the process. So why not? Okay, so now X and Y are perfect. To the spindle bearing rotation, now we need length. In order to establish the accurate length of the tool, what I'm going to do is I'm going to take a fresh end mill, I'm going to cut a surface on pallet 14 on this piece of aluminum I have in here. I'm going to take the fresh tool, I'm going to very lightly skim cut at a known depth, and then I'm going to come in and probe, and now the previous end mill that cut that surface is the reference to the probe, and then they will be in line with each other because that end mill is clean, it's fresh, it was calibrated on the laser tool setter right there, and that is how the manual says to do it. So you close the door, you push the button, now the door is locked, robot is ready. I go to my MDI screen, I go cycle def 340 workpiece number 14 because I want pallet 14. Cycle start. Machine goes to the corner. Door opens up. Robot goes up. And then oh, it's got to change grippers. Here, I'll show you. Nope. Duh, it's got to remove this pallet first. So this is a 72 millimeter small pallet, which I have on that side of the pallet changer. This side has 148 millimeter pallets. So that's going to put that back right there. And now it's going to release that gripper set. It's really sweet how it does this. It's so simple and clever and accurate. Grabs the big gripper. Rotates around to the other side. Comes and grabs pallet 14. Look at that. I love it so much. Then it's going to chill, it's going to wait right there for the next cycle. Door closes. Rotate 90 degrees to the home position. We are ready to rock. Let's go over here and check out the tool that I'm using. It's just this one, number 2. It's a 3-flute, uncoated aluminum cutting end mill, just super sharp. The only thing I ever use it for is this, which means I know it's in good condition. So I'm going to clean it with the Rodico putty. Do it right now. Make sure there's no oils or greases or anything on it. I'm going to set it on the laser tool setter. Actually, you know what I'm going to do first? I'm going to calibrate the laser tool setter with the calibration pin. Haven't done that in a while. It's good to do first before you do any major calibration comparisons. To calibrate the laser tool setter, make sure everything's dialed, we have a calibration pin, which is a very known ground diameter and a ground height. So we call up tool 10 and then we call up touch probe 581 calibration cycle. Tool 10 is already called calibration cycle. You can see the red laser dot on the part. Now it's getting the other side. Now it's going to get the bottom. I need more zoom. And then it's going to get the top edge. And I think that's about it. That thing has to be clean, clean, clean. And it is. Now I'm doing the exact same thing to that tool 2, the 3-flute end mill. Not the same thing, but I'm touching it off. It's grabbing length and diameter. There goes diameter. It's going to get it from both sides. When it goes to the other side, we might be able to see the red line on it. Kinda. Sweet, let's see if this value specifically changes. It did not change. Okay, length is 06302, and that's what I wrote down, 06302. Length is 3.86041, 3.86050. So we're talking 1/10, 90 millionths difference in length from before. So I'm glad I reset it, but that's really close. So now I'm just going to manually go down, do a skim cut at a 0 height and set some work coordinate at 0. Okay, here's what I'm going to do. Normally, for every single program I ever run, I run from preset number 10. It's like your work coordinate system. X0, Y0 because it's center of rotation, and then that's my Z height arbitrary value, but it is what it is. I'm going to enter preset 6, which is my temp. Always label your presets if you can, your offsets, so that you know what you're doing. Also X0, Y0, but the Z can be, notice how it's plus like 5 inches above my negative 153. And that kind of makes sense, because my 0 is way down there, and maybe that is about 5 inches, but regardless, I'm going to reset it as this. So I click on 6, and I click Activate Preset, and then I click Execute, and now I am in preset 6, temp, right there. So I'm going to manually activate the spindle. I'm going to manually jog it down and jog it over, and I'm just going to do a light little skim cut, not while holding the camera. So while the end mill is still spinning, it has made the cut. I left it there, I didn't lift it or move it or anything. My Z is currently at plus 0.1 inch, but I need to reset that to be 0, so that now the machine thinks, based on that tool's length, that surface is 0. Then I come in and I set the probe on that surface, and I calibrate the probe based on that surface. And that is a super easy process in Heidenhain. You just go find the menu called Set Preset. I want Z, not X or Y or B or C. I want Z. I want to set it, so it's at 0.109 right now. I want to set it to 0 and just click OK. Now watch that change. Boom. Now the machine knows that that surface is 0 based on this preset, that tool, everything. Now I just go in, I touch the touch probe, quick cycle start. Does some tool changing magic action. Right now, while it's waiting, the robot arm is grabbing the tool. There we go. Open the door. Blow this off. The probe positioned exactly over that cut surface. We're going to go over here to the jog side. Jog. We're going to scroll over until we see the touch probe button. Click on that. These are all your regular touch settings, measurement settings. We go over one more time. Calibrate touch surface. We want a straight down calibration, just like that. We're calibrating. Tool 20. Old calibrated length, diameter, doesn't matter. We're going in the Z- direction, and then I just click cycle start. Here we go. That's it. Not very exciting. But it is cool, it gives you your data. So, old calibrated length is 5.32, new calibrated length is 5.55. The reason for the huge discrepancy is before I had a 15 millimeter tip and I installed a 20 millimeter tip because that's all they had in stock. So it's a longer, that's why it's 5.32, 5.55. I hope that's close to 5 millimeters. Yeah, that's why. So now I click OK to confirm. And then now, my new calibrated length, if I jump into the tool table, tool 20, 5.55. Okay, I have two more calibration things I have to accomplish. Number one is, remember how I said the ball doesn't necessarily have to be on center? There's a calibration routine for that, so we're going to do that calibration routine, get the machine to know exactly where that center line is, and then next we're going to do a kinematic calibration where the whole machine table calibrates itself. So that's more of a kern thing, not a probe thing, but it uses the probe to do that, so like everything's got to be perfect. So let's do the first one. We're going to call pallet 3. There's actually little air blasts that come up and blast the bottom of each feet so that crud doesn't get underneath them. And it actually uses that air pressure to tell if the pallet is seated fully. Otherwise it will alarm out. So that's pretty cool. This, my friends, is a super precision ceramic tooling ball. 20 millimeters. Super polished, ground, shiny, whatever they do to it. It is mounted on a plate off-center, which is kind of important, as you'll see in the calibration routine. However, to get the tip center line calibrated, all I gotta do is I gotta put it roughly up here, and then it's gonna do whatever it's gotta do. Got the probe jogged just beside the tooling ball, roughly halfway down. And just like how we did the length calibration, we go into this touch probe menu. Not the regular routines. We go over here, we go calibrate, tool setter, touch, and then instead of the length setter, wrong one, we go to this one with the tooling ball button. Okay, 0.787 is my 20 millimeter tool, and it wants a starting angle of that way of 0 from this direction, not 45 or whatever. And then I just go cycle start. And it should, nope, did not. Oh, it wanted to be on the top center. I put it on the side, duh. So I stopped it, and then I can just jog it up. That should be close enough. Same. Let's try this now. It's finding itself. That's really cool. So it's going gently up and down and trying to find the highest point before it truly starts going around the outside. Yes, that is so cool. Do it again, probably a 180 rotation. You can see the LEDs kind of flickering and flashing, and there's a receiver there that is receiving the wireless data signal. Are we done? I think we're done. And just like before, we have a new, so same length, new calibrated radius. Before it was radius was 0166, and now the radius is 0151524, whatever. This is a different manufacturer, a different ball. It's a little smaller than it's a big radius difference. And then this, specifically the calibrated offset in X and Y. So a 1/10 and a 1/10, which is, I thought I had it closer than that. Previously it was 1/10 plus and 40 millionths minus. That's what it tells me. So something's not feeling right here. According to that data, the diameter of the ball, it's supposed to be a 1 millimeter ball. I'm measuring 0.77444 millimeters. That's 25% smaller than it's supposed to be. Something doesn't feel right. So I took my Mitutoyo Quantum mic and I mic'd it, and it is miking 0.3935, and if I hit the metric button, I think I pinched it too hard, but it's 1. It is 1 millimeter, like exactly. So because the diameter of the ball is calibrating and probing under what I think it should be, I'm just a little confused here, I set a work coordinate number 5 as the center and the top of that calibration ball, and then I'm touching around the outside of it to find your 0 line, and also measuring the diameter of the ball. So I've done this 4 or 5 times, trying to see the consistency and the accuracy of how close the current can probe that ball and still think it's on center. And the last time I did it, it thinks our ball diameter or ball radius is 39333, and our deviation from the last center line is 10 millionths and 9 millionths of an inch. That's insane. And I've seen this a couple times. Last time it was 11 and 7 and millionths of an inch of consistent repeatability of finding the center of that circle of the ball. That's really cool. But even still, this is reading less than what it should be. Right? It should be reading 3937, but it's reading 3933. So like 8/10 different than what that ball actually is in real life. Because that ball is 3937, but it's measuring 3933. It's not a huge difference, but it's something, and 8/10, it's measurable. I need to know what's going on. I'm probably doing something dumb. I found the calibration certificate for the tooling ball, and then it is measuring, they measured it specifically at 20 millimeters plus 4 whatever, and I converted that to inch so that I can do. And it's measuring just 10 millionths more than I thought it was, but that's something. So I'll put that into my calibration and then try it again. Alright, so being stuck on these weird numbers, I thought about it for a while, and then I texted my WhatsApp group of other machinists and friends of ours that's literally called Top Secret Machinists Group. Oops. A bunch of buddies from all around the world that are similar to me, and we all get along. So I asked them, gave them a bunch of info. I said, what am I doing wrong? I feel like it's not adding up. Something's wrong. So my buddy Lauren suggested, instead of measuring the tooling ball to establish the diameter of the ball and concentricity and all that, he highly recommends a ring gauge, which I have literally right here. So this is a precision ring gauge that has a calibrated diameter of 19.9999 millimeters. I'll clean the inside and I'll magnet it to the pallet right there and try this. Have the probe inside the ring gauge, and we go again here to the Calibrate TS. We are going not the ball, not an outside, but we're going an inside surface. We have to set the hole diameter, which 19.999 is that. That is my converted metric to inch. Starting angle 0, number of touch points 8. I think it only allows 8. More the merrier, I think. And then cycle start. So I noticed in this time it's not rotating the spindle every time, it's keeping it static, and I bet you it's going to come around again and rotate in a bunch of different ways. Being a calibration setting, it probably does all kinds of weird stuff. Okay, so after calibrating the diameter of the ball and the location of the ball in the ring gauge, I got almost the same results. Like the ball diameter was still quite a bit smaller than it was supposed to be. However, it compensated just a little bit differently, and then I went on the same ring gauge and I measured the diameter accurately with the current cycle, and it's measuring 6 millionths of an inch off from what's printed on the thing. So that is perfect. That is nothing. Absolutely nothing. That is 0 point and then 5 zeros and then a 6. It's crazy. So I think it works. I think it works much better in the ring gauge than on the ball. Ugh. It makes so much sense. I just totally forgot about the tooling ball, or that thing, the ring gauge. Duh. That's how I did it before. I just forgot. Excellent. So those measurements actually make sense. I measured the ring gauge 6 millionths. It's perfect. Next thing is to do a kinematic calibration of the machine where it moves and does all kinds of stuff. So I have set up, I brought back the calibration ball. I moved the probe tip to just above it, and we're gonna go into MDI. Touch probe 550 Kern ball Kinematic. Run that cycle. It should just work. It's not working. Function not permitted. I remember. My machine is an inches. This function only works in metric mode. So I remember now, I brought in a program before that I've called Kinematic 550, so it's an actual machining program. And this is how you set in the program millimeters versus inches, mm versus INCH. So now this program does my stuff, and I wrote notes to myself so I can read. Very important, because if I'll have to read through that carefully. Only works when programmed in metric, and then it runs, calls pallet 3, calls the touch probe, moves to certain positions, and then runs the probe 550 command, just like before, and then goes home and everything. So this program does everything I need to do. It worked before, I trust it, but I'm going to read through this anyway. So those notes are reminding me to do the kinematic calibration first, then go back and calibrate that tool 10 to calibrate the laser, because otherwise I had a problem doing it the opposite method first. Calibrate the laser first and then do kinematic. I don't know. That's what my notes say. So I will do the kinematic first, and then I'll go back and calibrate the laser again. Okay, so I'm coming in real slow. This is the program. It went home first. Now it's coming in here. It's going to ask me, there's a menu on the screen, is the touch probe centered and about 5 to 10 millimeters above the ball? Yes. Now, it's coming down, it's going to hit the surface. It's coming down, it's going to hit that side. And it's going to do this for a couple minutes. So let's pull a time lapse and you guys can see. So what that does with all those cool movements where it's probing and rotating and going all around, I love that stuff. It's checking it knows that ball is 20 millimeters. It's checking the location of it in this position, in this position, in this position, and comparing the actual movement of the machine and the travel of that ball through space with where it thinks it's supposed to be. And deep inside the kern, in the brain, in the computer, it's calibrating for those movements kinematically. Pretty sweet. So apparently one of my buddies does that every Monday. Like, there's literally a scheduled routine in the machine where every Monday it'll call that program, call that pallet, and just do it. I will just have to remember to do that fairly often. It's been a little while since I've done it, so. Cool, guys. Looks like we're back in action. That took a lot longer than I expected. This short video turned into a not short video, but that's normal. And good to be back in action. I got parts to make. Later.